In this video, you're going to understand the first fundamental theorem of calculus, which does say if f of x is continuous on the interval a to b, which looks like it's a closed interval, and if little f is the derivative of big F, then the integral from a to b of f of t dt is capital F of this b minus capital F of this a. So you do have to first understand that the f's mean different things. So if we look at this graph of little f, and we're going to call it a velocity graph versus time graph, we already know what the derivative of little f would be in terms of its label. We know derivatives in general are the slope of a curve at any one point. So if we said the derivative here in theory is slope, change in y over change in x, we're basically saying the derivative of this is miles per hour over hours, which we should know at this point simplifies to miles per hour squared, which is an acceleration label. So the derivative of this function is acceleration, and since the slope at any one point is 0, we're seeing that the acceleration is 0. It is going 50 miles an hour, this object, but its acceleration is 0. Now we want to talk about more where capital F comes from, because this is the derivative of little f, so that's not in the definition. So you do not need the derivative of this function to do the first fundamental theorem of calculus. You need to think more about what capital F is, okay? So basically, if we were to start with some object that in the beginning didn't have a speed, that's why I did it as a discontinuous function. And that means that after 1 hour, the speed is 50 miles an hour. And at 2 hours, you're still going 50 miles an hour. And even at 3, you're going 50 miles an hour. So what I want capital F to represent is basically the integration, right? So the integration of little f, we already knew was the area under the curve. What does the area under the curve represent? So if I, for instance, wanted to go from 1 to 3 of this function, I would integrate f of x dx from 1 to 3. So right now, if I look from 1 to 3, I can see the integration, which is the area under the curve, is an exact value. I don't need Riemann sums for this. And basically, I can say that it's 2 by 50, so that's 100. And the label of an integration of mile per hour times hour, when you multiply velocity times time, you get distance, which is miles. Because of course, stoichiometry, miles per hour times hour will just give you miles. Now, in terms of getting back to the fundamental theorem of calculus, if capital F is what we're looking for, that means this is a position or a distance. All right, some people use the word position. A lot of people are very comfortable saying it's the distance traveled. So if you think about this object who was going really nowhere in the beginning, so there was no change in distance, but after an hour you went 50 miles. So at a second hour of 50 miles an hour, you would have gone 100, and after 3 hours with another 50 miles an hour velocity, you went 150 miles altogether. So this is not here at all. This capital F is not in this picture, but it is the integration of velocity. So you will notice that instead of looking at a graph and doing it by the area under the curve, you can actually use this new first fundamental theorem of calculus. The integration from 1 to 3, for instance, to get 100, if you took f of 3, which was the 150, and you subtracted f of 1, which is the a, and 50, you'll see you get that 100 miles. So the fundamental theorem of calculus will allow you to integrate without actually finding the area of the curve once we understand how to get backwards from little f back to the derivative of f. So instead of derivatives, which is of course the derivative of velocity is acceleration, how do you go backwards from velocity back to distance? We have to concentrate on an antiderivative, and that's what we have to start learning tricks for next.